So, I would like to welcome you to Lecture 7 of EE to FH3. We'll start the electrostatics part in this lecture. We have now all the foundations that we need from vector analysis, and hopefully we can build on that to see how we can get and evaluate electrostatic fields in different parts of the space due to different types of charges. Okay, in this lecture we'll cover the definition of electric forces. And then we'll talk about electric field. We'll talk about how we can get the superposition of electric field, different types of electric fields due to discrete set of charges. We are covering chapter 4, pages 107 to 115 of the textbook. Here in this part, to remember a few things about charge and about material. Matter in general. So we know that the electric charge is a fundamental property of matter. Any material has many atoms in it, and the atoms have electrons. And we measure the charge in terms of coulombs, the unit of measurement of the charge in terms of coulombs, and this after the name of the French scientist who was able for the first time to show that bodies with different charges do either attract or repel depending on the sign of these charges. In SI units, the unit of measurement of the charge, which is a coulomb, is actually is a derivative or based on the unit of the current, because current by definition is the negative of the rate of the rate of change of the charge. So if you have a certain volume and the charges are leaving that volume, then the total charge is decreasing, and this change is creating a current. So we defined, so the relationship is that the Coulomb, as shown here in this equation, Coulomb is equal to ampere second. So when we say there is a current of 5 amperes flowing through a certain cross section, this means that we have 5 coulombs leaving per second. And it should be clear that one coulomb is a big charge, is not a small charge, and I will show you this later when we talk about the charge in just one electron. So here we keep in mind that the coulomb, the unit of measurement of the charge, is called the coulomb, as shown here, and it's based on the unit of measurement of current, and this is in the SI units. System International, in which the length is measured by meter, the mass is by kilogram, and so on. So keep this in mind. The current is measured in amperes, charge is measured in coulombs, and current is really the rate of change of the charge with a negative sign here. This, of course, included the direction. So in the universe we have positive charges and we have negative charges. We have electrons and we have protons. And these two types of charges will act differently when they are under the influence of electric fields. You will know later in electromagnetics and in maybe in semiconductor courses as well that the positive charges drift in the direction of the electric field, while negative charges drift opposite to the electric field. Protons, they have positive charge. Electrons have negative charge, and these two have the same charge in magnitude. So in magnitude they have the same charge, but in sign they have opposite value. And the charge in one electron, which is the smallest indivisible charge in the universe, is tiny, is minus 1.6 10 to the minus 19 coulomb. And you have to remember this number. This is the charge in one electron, minus 1.6 10 to the minus 19 coulomb. And you see, to get one coulomb, you need how many electrons? Huge number of them to get a charge of one coulomb. We will focus here in this course on charge distributions in dimensions larger than that of the atomic dimensions, 10 to the minus 15 meters. So we'll assume that we're talking about charges in much bigger dimension than those of the atoms. One type of charges that we'll see very often in this course is the concept of a point charge. There is nothing really called a point charge because the charges always exist in a finite volume. And within this volume they may have a varying density. So as we explained earlier in some of the course, on some of the examples, you may have a certain volume and charges do exist inside this volume. They can become dense in some parts and less dense in other parts. But if we look at a certain volume as happening here, this is a volume, but we look at it from a very far distance, it looks pretty much like a point. And in that case, we say we can consider it as just one point charge whose value is the total charge inside this small volume. So we can multiply the volumetric charge density, which can be assumed to be homogeneous or uniform by the volume, which may be small in this case, to get the total charge. So to keep in mind, when I talk about a point charge or when I talk about a discrete charge, I effectively mean a volumetric charge, but it's the volume of this charge is much smaller than the dimensions at which we are measuring the field. So where actually the distance at which the field is being measured is far from this charge to the extent that we can consider this volume to be just a point. So just keep this in mind, because very soon we'll be discussing the electric field resulting from a point charge. It was a French scientist, Coulomb, who discovered for the first time that if you have two bodies and each one of them has a charge on it, whether it's positive or negative, they either attract or repel according to a certain law. And this law became the law of Coulomb. And the basic idea here in this law, if you take a look at this diagram here, we have a charge Q1, which has a position vector R1 from the origin. So there is an origin here, and charge Q1 is located at the location R1. And here you have a charge Q2, which is at position vector R2. These charges may attract or may repel depending on their sign. Similar charges do repel. So if these two were positive, you will see that there is a force between them trying to push Q1 in this direction and trying to push Q2 in this direction here. So, but if one of them has an opposite sign to the other, they will see that they are both trying to attract. So Q2 will be pushed, will feel a force in this direction, and the Q1 will feel a force trying to attract it to Q2 in this direction. And the forces, it was Coulomb who was able to put these forces for the first time in a mathematical expression. And this mathematical expression is given by this formula here. So what is F12? F12 is the force affecting Q2 as a result of Q1. So the charge Q2, which at the location or position vector R2, feels a force F12, which is due to the presence of Q1. And also Q1 feels a charge, we call it F21, which is due to the presence of the charge Q2. And these two forces are always opposite to one another. So if the two charges repel, Q2 is being pushed in this direction, and Q1 is being pushed in this direction. As you could see here, that the direction of F12 is opposite to the direction of F21. But if these charges are opposite and they attract, Q2 will be pushed in this direction towards Q1, and Q1 will be pushed in this direction towards Q2, and again these two forces are opposite to each other. So what is the expression here? There is a constant that Coulomb was able to determine. This constant K has a very large value. It is I will show you this value later in the next slide. But just keep in mind there is a constant of this constant here. The value of the first charge, the value of the second charge, divided by the square of the distance between them, and this unit with this force which is affecting Q2 due to the charge Q1 is pointing in the unit vector, in the direction of the unit vector A12, pointing from Q1 to Q2. So A12 is the unit vector pointing from here to here, is in the direction of R12. This is where our knowledge of vector analysis will be very useful to determine the direction of all these forces. So, so here just keep in mind the number of things. There is a constant K, which I will show you its value later. It's a very large number. There is a value of the first charge, value of the second charge, divided by the square of the distance between them. And this force F12 is in the direction A12, where A12 is the unit vector pointing from charge Q1 to charge Q2 in the direction of the vector R12. So R12 is, again, according to our vector analysis, R12 is R2 minus R1. The length between the two charges is simply the magnitude of this vector. And the A12 is obtained by dividing this vector by its length. So these are the elements that you need to know in order to calculate the force between any two charges. So the force is proportional to the value of the two charges, inversely proportional to the distance between them, and it's pointing in the direction from the first charge to the affected charge. So according to Coulomb's law, you can see if two charges are positive, they do repel. So this is charge Q2 will be affected by force here F12. Charge Q1 will be affected by force F21, and they are pointing opposite to each other, trying to push these charges away from one another. If these two charges are negative, they are also going to repel, and you can see F12 is pushing Q2 in this direction, F21 is pushing Q1 in this direction, and they are trying to move apart from one another. But if one of them is positive and the other one is negative, and it doesn't matter which one is positive, which one is negative, you will see that the charge affecting Q2 will be trying to pull it closer to charge Q1. The charge affecting Q1 is which is really F21, is trying to pull it closer to Q2. So this is, as I said, this expression here that we have for the charge. The only difference here is that I removed the unit vector, I replaced it by the vector divided by its length. So here, instead of having the length to the power 2, it became the length to the power 3. So this is very important to understand that this is exactly equivalent to the same form I've shown you in the previous slide. So the vector R12 is simply the vector connecting, is pointing from Q1 to Q2, so it's equal to R2 minus R1. And this here is the norm divided by 3. So now this is not a unit vector anymore. So it is a vector, and then we divide by one more norm. The constant of proportionality was measured by Coulomb, and it was found to be equal in vacuum to 9×10 to the power 10. And this constant is actually does change with the change in the material. So if the two charges in a different medium, say they are inside wood, say they will feel different forces than the one in air or than the one in water. Okay, so this constant of proportionality, which is K, is really dependent on the material type. So as I explained, this constant K is 1 equal to 4 by epsilon, and the epsilon is actually a property of matter. It's called the dielectric permittivity, and this one you have to remember very well, because we will see it over and over and over again in electromagnetics. It's a property of matter, and it doesn't change from one material to another. In vacuum, this value of epsilon naught has this number, which you have to remember, 1/36 by 10 to the minus 9. This is the one I remember usually. I don't remember this expanded version. It's in farad per meter. It has units farad per meter, and farad is a unit of measurement of the capacitance. It is Coulomb per volt. So this is expansion here of the units, if you want to take a look at that. For a general medium, the permittivity of any medium is equal to that of vacuum multiplied by a constant called the relative permittivity, or relative dielectric constant. It's called epsilon R, relative permittivity or relative dielectric constant, and it is usually greater than 1. For air, the relative permittivity is very close to 1, and in all problems that I'm going to be giving you, unless mentioned, you have to take your medium to be air or vacuum, and in that case epsilon R is 1, and your permittivity is that of vacuum, which is 10 to the minus 9/36 pi. Otherwise, if we are using a different medium, I will be telling you what is epsilon R. If you know epsilon R, for example, for water is equal to 80, then you are able to know what is epsilon, because epsilon is equal to epsilon naught epsilon R is equal to the permittivity of free space multiplied by the relative permittivity. So keep in mind, every material is characterized by some relative dielectric constant, and this number is usually greater than 1. And when I give you the relative dielectric constant, in order to get the permittivity, you multiply by the permittivity of free space, which is 1/36 by 10 to the minus 9. and the permittivity changes from one material to another. And in our bodies, the permittivity of the skin is different from the permittivity of the bones, is different from the permittivity of say the blood is different from the permittivity of fat. Every type of tissues will have its own water content, and the water content affects the value of the permittivity. So this is what you have to remember. So remember this constant of proportionality. The K, when I say it is the value I gave you earlier, then this means it is for vacuum. But for other medium, for other type of material, we have to take into account this relative dielectric constant. Now let's take a look at a couple of examples. This one here, we have a 10 nanocoulomb charge located at the 0, 0, and 4 meters. And so this is in Cartesian coordinates. And a 2 nanocoulomb is located at 0, 4, and 0 meters. So this one of them is located on the z-axis. This one is located on the y-axis. We would like to find the force acting on Q2 due to Q1. So as we agreed, there will be a force between them. These two are two positive charges. So the force will be a ripple force trying to push them apart from one another. In order to find the charge acting on Q2 due to Q1, we have to find the unit vector pointing from Q1 to Q2, and this will be the direction of the force. And of course, we use Coulomb's law to get the value of the force. As I mentioned several times, it's usually helpful to start by drawing a diagram to get a better understanding of where the charges are, where the forces are. So here you have the charge Q1. It is on the z-axis at a height of 4 meters from the origin. The charge Q2 is in the y-axis at a distance 4 meters from the origin. And if you see the force affecting Q1 and Q2, you'll see Q2 is trying to push Q1 away from it. So the direction of the force, which is this one here, which is R12, will have only a component in the YZ plane. It does have a component in the X direction because both the charges are in the ZY plane. And you will see here that this force here, which in direction R12, will have a positive Y component and a negative Z component. So this will give me more understanding of the result that I'm going to be getting. So what we have to do, we have to first find R12. R12, as we have learned from our vector analysis courses, is equal to R2 minus R1. So we have to reverse the order. And once you know that, you apply Coulomb's law, the product of the two charges divided by 4 pi epsilon r divided by the square of the distance in the unit vector pointing from here to here, and this will be the value of our force. So here first I started by calculating R12, which is the vector pointing from the first charge to the second charge, is equal to R2 minus R1. So it's equal to 0, 4, and 0 minus 0, 0, and 4. So this will give you this vector. This is R12. And if I use the form of Coulomb's law that requires a unit vector, I have to find the unit vector in this direction. So how do I find it? I simply divide the vector by its magnitude. So this vector will have a magnitude of a square root of 4 squared plus 4 squared, and this will give you 4 square root 2. So if you cancel 4 with 4, this will be your unit vector pointing from the charge Q1 to the charge Q2. And this gives you the direction of the force affecting Q2 due to the presence of Q1. And of course, if I ask you for the charge affecting Q1 due to the presence of Q2, it is the opposite of this force. So we move to apply Coulomb's law. So Coulomb's law is telling us that the force affecting Q2 due to the charge Q1 is equal to Q1 Q2 over 4 pi epsilon naught. Remember, I didn't tell you anything about the medium. In that case, you have to take the medium to be air or vacuum. So epsilon r is equal to 1, and you have to use epsilon naught, which is a permittivity of free space or of vacuum, 1 over 36 by 10 to the minus 9. This is a unit vector pointing from the first charge to the second charge, and this is a distance squared. Now, when you substitute in these expressions, you get many terms, and you have to be careful. Don't make a mistake when you cancel them. This is the value of the first charge, 10 nanocoulomb. Remember, nano is 10 to the minus 9, so it's a very tiny charge. 10 nanocoulomb. The value of Q2 is 2 nanocoulombs, so this one here. This is 4 pi multiplied by epsilon naught 1 over 36 by 10 to the minus 9. The distance between the two charges, we have found it earlier. It is the norm of the vector R12. So it is 4 square root 2. We square that. This is the unit vector pointing from charge Q1 to charge Q2. So things can simplify. These two will cancel out, will give you 9. 9 will go up to the numerator. 10 to the minus 9 will cancel with 10 to the minus 9. Then you get 9 multiplying 90, multiplying 2, dividing 4 square root 2 squared. When you do all this and you divide by square root 2, you get 3.977 nanonewton. So the answer, that the unit of force is in newtons, but because you get another 10 to the minus 9 that remains, then the force will be extremely weak. It is nanonewton. So the answer here, as you could see, as I predicted, the force is trying to push Q2 away from Q1. It has a positive Y component, it has a negative Z component as predicted earlier. So again, drawing a diagram will help us to see whether our answer makes sense or not. Here we see a second example where we would like to find the force exerted by a 100 nanocoulomb charge. So this is a little bit bigger charge, which is located at the origin at 0, 0, and 0 meters on a 3 nanocoulomb charge located at 4, 3, and 2 meters. And if I don't tell you it's in meters, it is given, you should assume everything, all the lengths given are will be in meters. So if I don't tell you, if I forget for one reason or the other, unless otherwise mentioned, all dimensions will be in meters. So this is another example. We have two charges. One of them is affecting the other by force. Actually, both of them affecting each other, but we usually try to find the force affecting here in the 3 nanocoulomb, affecting it by due to the presence of the 100 nanocoulomb. So as I explained earlier, you should start your answer by drawing a symbol diagram to see where the charges are and to see whether your prediction of the force will be right. In this example, the charge Q1, which is a big one, is in the origin, and this is a smaller charge which is located somewhere in space at all positive coordinates of x, y, and z. And of course, the direction of the force, because of them are positive, is trying to push Q2 away from Q1. So it's trying to move it in this direction of R12. R12, as we agreed, it is a vector pointing from the location of charge Q1 to charge Q2, and is equal to R2 minus R1. But luckily R1 here is the origin, so R12 is nothing but R2. So it's equal to 4ax plus 3ay plus 2ez. And I can predict here that this force will have all positive components in the x, y, and z because of the location of the two charges. The unit vector in the direction of R12, which you will need in Coulomb's law, is equal to R12 divided by the norm of that vector. So this is a vector here divided by its norm, and its norm is square root of 4 squared plus 3 squared plus 2 squared. So this will give us here a square root of 29. This is 5.385. So if you divide this vector 4ax plus 3ay plus 2ez divided by this number, this is what you'll end up having here as an answer for your unit vector pointing from charge Q1 to charge Q2, which will be the direction of your force, because both of them are positive charges and both of them will repel. So the last step is to apply Coulomb's law, and you see that the force between the two charges is proportional to the product of the two charges divided by 4 pi epsilon, and the epsilon is the permittivity of the medium, the distance squared between them in the direction of unit vector pointing from the first charge to the second charge. The first charge, the big one, which is in the origin, is 100 nanocoulomb, so 100 by 10 to the minus 9. The second one, I think it believe it was 3 nanocoulomb here, so this is 3 10 to the minus 9 divided by 4 pi multiplied by epsilon. And because I did not say anything about the medium, you should assume it is vacuum or air. It doesn't matter. The epsilon R of air is very close to 1, so we take it usually to be 1. So this is 1 over 36 by 10 to the minus 9. The distance between them, if you remember, we calculated earlier to be square rooted of 29. So this square root of 29 is squared, so it gives you 29. A12 is a vector pointing from charge Q1 to charge Q2. So if you simplify all these terms, you'll see 10 to the minus 9 will cancel 10 to the minus 9. These two will cancel, will give you 9. So you get here 900 multiplying 3 divided by 29. So you end up with this expression here, and then please verify my answer. I may have made a mistake here or there, and one of these 10 to minus 9s will remain. And if you multiply everything, if you multiply by A12 from the previous page, you get this answer here for the charge, and it's again it's nano Coulomb because you have here 10 to the minus 9. So this is a force affecting Q2 due to Q1, and as I predicted, this force has all three positive components. So it's trying to push it from the origin away in the first octant in the Cartesian space.